In this video, we'll be implementing a convolutional neural network, one of the most well-known deep learning algorithms for image processing, using code. Specifically, we'll apply a CNN model to the popular image classification example, the MNIST dataset. This slide shows the overall flow of how we'll build and implement a CNN to classify the MNIST dataset using code. To explain in more detail, the MNIST dataset consists of 28 by 28 pixel grayscale images. First, we apply 32 3 by 3 filters with a stride of 1. As explained in the previous video, this results in an output size of 26 by 26 with 32 channels. Next, we apply 2 by 2 max pooling without padding, which reduces the output to 13 by 13 by 32. Then we apply 64 3 by 3 filters with a stride of 1, resulting in an output of 11 by 11 by 64. Again, using 2 by 2 max pooling without padding, the output becomes 5 by 5 by 64. Finally, this output is flattened into a one-dimensional vector of 1,600 values, which is passed into a fully connected layer. At the output layer, we use the softmax activation function to perform classification. All right, let's go ahead and implement this in code. The code file is available on GitHub, so you can download it and try running it yourself. First, we import TensorFlow and the necessary libraries for building the CNN model, along with the MNIST dataset. Then, we load the MNIST dataset and split it into training and test sets. As you can see, the training set contains 60,000 images, and the test set has 10,000 images, each of them sized at 28 by 28 pixels. First, since the X data consists of pixel values ranging from 0 to 255, we divide by 255 to normalize the values between 0 and 1. Next, we use the toCategorical function to convert the labels into one hot encoded format. After that, we reshape the data using the reshape function to match the input format required by a CNN. Originally, each MNIST image is a one-dimensional vector with 784 pixel values. To feed it into a CNN, we reshape it into a 28 by 28 two-dimensional image and also specify the number of channels, which is 1 for grayscale images. Here, the -1 in reshape tells the program to automatically determine the number of samples based on the input data. In the diagram below, we first apply a convolutional layer, followed by a max pooling layer, then repeat the same process, another convolutional layer and max pooling, before passing the output to a fully connected layer. To build the CNN model using the sequential API with the add method, we start by creating a sequential model. Then we add each layer, one by one, using the add function. First, we add the initial convolutional layer and a max pooling layer. Next, we add a second convolutional layer, followed by another max pooling layer to extract deeper features. After that, we use a flatten layer to convert the multi-dimensional feature maps into a one-dimensional vector. This is followed by a fully connected layer with 64 nodes, and finally, a softmax output layer that classifies the input into one of 10 categories. Let's take a closer look at this part. Conv2D is a layer in Keras that performs 2D convolution operations. It's commonly used for processing images. In this line of code, the number 32 refers to the number of filters, and kernel size means that each filter has a size of 3 by 3. The input shape parameter specifies the shape of the input data. Since MNIST images are 28 by 28 pixels and are grayscale, the input shape is set to open parenthesis 28, 28, 1 close parenthesis, where 1 stands for the number of channels. The padding equals valid part means that no zero padding is applied, so the output size will be slightly smaller than the input. If you want to keep the same output size as the input, you can set the padding to same instead. We can use the model.summary command to check the structure of the CNN model we've built. The first convolutional layer outputs a feature map of size 26 by 26 with 32 channels. The following max pooling layer reduces this to 13 by 13 by 32. Then, the second convolutional layer produces an 11 by 11 output with 32 64 channels. And the next max pooling layer brings it down to 5 by 5 by 64. The flattened layer then converts this into a one-dimensional vector with 1,600 values, which is followed by a dense layer with 64 nodes, and finally, a softmax output layer with 10 units for classification. As you can see, this matches the structure shown in the diagram below. In this code, zero padding is not used, and as a result, we can see that the size of the feature maps gets smaller after each convolution operation. For example, when the input image is 28 by 28 pixels, the first convolutional layer reduces the output size to 26 by 26, and it becomes 13 by 13 after max pooling. In the second convolutional layer, the size is further reduced to 11 by 11. On the other hand, if we use padding equals as aim to apply zero padding, the output size remains the same as the input after the convolution. So, after the first convolution, the output would still be 28 by 28, and after pooling, it would become 14 by 14. The second convolution would also keep the size at 14 by 14, 14 in this case. Now let's compile the neural network model we've built. We'll use the Atom Optimizer as our optimization algorithm and set the learning rate to 0.001. Since the class labels are one-hot encoded, we'll use categorical cross-entropy as the loss function. For evaluating the model's performance, we'll use accuracy as the metric. Next, we train the model using the training data. We set the number of epochs to 30 and the batch size to 32, meaning the model will train on 32 samples at a time. Also, we allocate 30% of the training data as validation data, so we can monitor how the model performs during training and check for potential overfitting. The training process will store information such as loss and accuracy in a variable called learning. As training progresses over multiple epochs, we can observe the loss gradually decreasing and the accuracy steadily increasing. After training is complete, we evaluate the model's performance using the test dataset. By using the evaluate function, we can check both the loss and accuracy on the test data. In this case, the accuracy is 0.9899, which means the model achieved 98.99% accuracy on the test set. This is higher than the accuracy achieved by a multi-layer perceptron model, showing that the CNN model performs better for this classification task.